the work energy principle. I'm not really happy with the way most textbooks treat the work energy principle, so I'm going to make my as short as humanly possible summary video about the work energy principle. Just a quick note, my ideas are influenced by other books. My favorite book, Shabai and Sherwood, Matter and Interactions. So it's basically that stuff. But let's just get to it. We have some stuff to cover. We have some prereqs. I made a little list so I wouldn't forget. So we're going to talk about forces and how you represent those as vectors, and just so that we can go through the different options. The dot product, a way to operate two vectors together. Then we'll talk about the work energy principle and why you would use that. We will talk about a very simple system and choosing systems, and then we'll do a complex systems, and then I'll talk about the types of energy, and then that'll be it. Now, and there's a whole bunch of stuff that you could do with this, and there's more complicated things too, but we're gonna stick to the basics, right? Basic stuff. Okay, so let's talk about forces. Remember that if I have some force, let's just even say it's some force F like that. How do I represent that force as a vector? Well, the easiest thing is to say, well, it has some x component this way, I call that fx, and it has some y component that way, fy. And so now, how do I represent that, write that down? You could even have it in a z direction too, right? That's the x direction, y direction, that's the z direction. But there's a couple ways that we could represent this vector. One is to write it like this. F is fx in the x direction plus fy in the y direction. Okay, so that says how much in the x, how much in the y. And you think, well, hey, I thought we're doing work energy. Why do we care about that? It's going to matter. Another common way is to write this as f as the x component, and then they use I hat plus the y component, and they do j hat. And then these both have a k, a z component, z hat. You could do that. Plus fz k hat. So those are really the same representation. In the first semester of physics, we like to do things in 2D because we can. But it's important to realize that we live in a 3D world. And in the second semester of physics, when you get to magnetic fields, you can't do it in 2D. It's a 3D thing. So I'm just letting you know. And then finally, the way I like to write it, this comes also from matter and interactions, is like this. So we can just write the x, y, and z as a triplet, fx, fy, fz. Okay, but these are all numbers, right? So they're numerical values. They could have numerical values for them. So I could have something like f equals, I'll write it in that format, 2 x hat minus 3 y hat. And then I could write that in my format as 2 negative 3 0. I'm going to always include that z direction just because it's easy. It doesn't really take up much room. So here I have 3 components, and it takes up as much space as that. It's all about the space, people. It's space. Okay. So that's how we one of the ways that we represent vectors. Here we're going to use two types of vectors, the force vector and the displacement vector, but they're both in that same format. Okay, forces, dot product. Now, we've already looked at forces before. We found the magnitude of a force. We found, we added forces, we subtracted forces. We multiplied the force by a scalar, right? If you did ma, that's a vector, but I multiply it by a scalar. That's cool. Okay, you can do that. But now we're going to do a new thing with the vector, and it's called the dot product. So this is a way, suppose I have two vectors. I have vector A and I have vector B. I can take the dot product, and what it really tells me is how much of B is in the direction of A, or how much of A is in the direction of B. It doesn't matter. You can do it either way. Okay. So we can define this. I'm going to go ahead and define this. Suppose I have the vector A. I'm going to write it in my format as AX, AY, AZ, right? It has an XYZ component. B has components. BX, BY, BZ. It has an X, Y, and Z component. Then we define A dot, see the little dot, B. That's not multiplication, right? Multiplication is for scalars. These are vectors. So you can't do multiplication, but you can do this operation, which is called the dot product. also sometimes called the scalar product. You can't spell it, right? It's right there below it. Why can I not spell it? Scalar product. There is another operation between vectors called the vector product, the cross product, but we don't need to talk about that yet. But this is important to know for that. So if I take A dot B, I get a scalar answer, and this is how I calculate it. I calculate it as AX, BX, so the product of the X components, plus the product of the Y components, AY, BY, plus the product of the Z components, AZ, BZ. That's it. And that's a scalar, 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 so I get a scalar value. Now, we're going to see that the dot product can be positive, it can be negative, it can be 0. Okay, so it can be any of those things. That's that. Now, there's another way to calculate it that's also very useful, and we'll talk about this too. Suppose I have the angle theta, that is the angle between the vector A and the vector B. Then I could write A dot B as the magnitude of A times the magnitude of B times the cosine of the angle between them. Like that. It's the same thing, okay? And so oftentimes we'll write this as just A, B, cosine theta. So I'm going to do problems, and we're going to do this both ways, but that's that. So forces, just a reminder of how we represent forces and the dot product. And you're thinking, what the heck? Why do we even care about the dot product? Well, we care. Okay. So now let's talk about this work energy principle. And I am going through this fast. If this doesn't make sense, that's fine. You know, things don't make sense right away. Okay. But let's just think about what we've done before. Mostly we've been working on this. F net equals ma. That's Newton's second law, right? So what we would do is calculate the forces on an object and use that to find the acceleration. Sometimes we'd go the other way, sometimes we'd know the acceleration. But let's just say we calculate the forces on an object and find the acceleration. And then, we know the definition of acceleration, so that's really mass delta V delta t. So I like this F net is mass delta V delta t, because that kind of gives us a picture of where we're dealing with things. First of all, we're dealing with changes in time. Newton's second law is really good at dealing with objects when we're talking about changes in time. Number one. Number two, force is a vector, velocity is a vector, position is a vector. So this is a vector equation, and that's really nice, right? It tells us stuff about how things move. Now let's just imagine that we had the following problem. I take a ball, and we're going to do this problem. I take a ball and I let it fall down a height h. And I want to say, well, how fast is that going? Well, I could calculate the force on this, right? It's gravitational force, and I could use that to find the acceleration. But then I'm like, well, how do I know how fast it goes after a distance? There is a kinematic equation that just gives that to you, that doesn't have time in it. But there's a couple steps if you think about it. You're talking about like finding the average velocity, and then using that average velocity to find how long it fell, and use that to find the position. Or actually use the position to find the time, and then use that to find the velocity. Of course, that assumes that we have a constant acceleration. You can't do that if it's not constant. So we made some assumptions there, but it's not a completely trivial problem. We may make it trivial, but it's actually not. Okay. So if we don't deal with time and we're dealing with changes in space, then it's a little bit trickier. In that case, we can use the work energy principle. Okay, so why would we use the work energy principle? Let me say what it is. So let me first define work. Work we define as W is the vector F, some applied force dot a displacement delta R. And now you could write that as F delta R cosine theta. See, there's those two definitions of the dot product, right? I have the vector version and the non-vector version. Either one's fine. But if I push on an object over some distance, then I'm going to do work on that. And that work is the change in energy of the system. And we'll talk about the system in a second. Okay? But more importantly, why would I do that? We would do the work energy principle because work is a scalar, that's a scalar value, and the change in energy is a scalar value. So that's the first thing. It's not a vector equation. The second thing is that this deals with a change in position, not a change in time. So when we're dealing with things, we don't really care how long it takes. We only care about it starts here, then we can use the work energy principle. So that's why we're going to use it. So it's a different way of thinking about things. Is it possible to solve a problem both with Newton's second law and work energy? 100%. Is one easier than the other sometimes? Yes. Or sometimes it doesn't really matter which one? Yes. If it was a test question and it didn't say to use the work energy principle and you solved it with Newton's second law, would I take off? I wouldn't. I didn't tell you, right? You solved the problem, you solved the problem. Someone else might, but they shouldn't. Okay. Let's go ahead and talk about choosing a system, because this says the work done on a system. So imagine that I have some group of stuff and I'm pushing on it. That is going to do work, and that work is going to change the energy of the system. But what is my system? It tells me what does work and what kind of changes in energy that we have. So let's just take the simplest case, the simplest situation, and do a problem. I'm trying to think, should I erase this? I'm going to erase this so I have more room. I like this side of the board better. So let's erase this side of the board, and then I'm going to use the work energy principle to find out the speed of a ball that falls. Simple problem, right? But it'll help us kind of think about all this stuff. And we can do it a bunch of different ways. So here's my problem. I have the ground. I have a ball. It has a mass m, and it starts up here, position 1. I'll call that y1, and it's going to fall down here to y2, and then this is a height h. And up here, the velocity v1 is 0 meters per second, and down here, v2 is I don't know. And I want to find that final velocity. So with the work energy principle, I think the most important thing, and a lot of textbooks drop this out, is the idea of choosing a system. So I want to pick a system. I'm going to go ahead and say it, system. What is, if I want to use the work energy principle, what am I doing it on? It depends, right? Okay, so in this case, I'm just going to pick the ball. That's my only system. So that means there's two things that are important. Any external interactions will do work. So the work is from external interactions. And then the change in energy depends on my system. In this case, the change in energy is going to be kinetic energy. So kinetic energy is 1/2 mv squared. So if I only have a point mass, it can only have kinetic energy. I mean, you could say it has, let's just say that. I'm not even going to say the more complicated version just to be right. I'm not going to do that. Okay. So it can only have kinetic energy if it's a point mass. That's all any kind of energy it can have. So we know what we need to find out what forces are doing external work on it, and we set that equal to the change in energy. Okay, let's start off with the work. So work is F dot delta R. Well, it's going from here to there, so I need to find delta R. Well, let's just write that out, okay? So I'm going to say up here, I'm going to say this is delta R. I need to find that. Delta R is going to be R2 minus R1. I'm going to do this as a vector, okay? So I'm going to pick down here y equals 0. This is my y equals 0 value. And then that's actually my origin. So that's y is equal to 0, x equals 0, z equals 0, 0, 0, 0. Okay. So down here, I can say R2 is equal to the vector 0, 0, 0. What about up here? What's my position up here? Well, R1 is going to be 0, h, 0, right? Because it's a height h. So if I go up h, that's where it would be. Well, now I can find delta R. Delta R is going to be R2 minus R1. And I can subtract vectors, right? R2 minus R1 is going to be 0 minus 0. 0 minus h is negative h. 0 minus 0 is 0. So now I have my delta R. And you don't actually have to do it that way, right? I don't really care about R. I don't care about R1. I don't care about R2. I care about the displacement. If you just said, oh, look, it moves down H, and you put negative H, that's fine. Okay. I like doing it this way because it shows you everything you need to know. Now, what about the force? In this case, what is doing external interactions on the ball? And that's the gravitational force. So I do have a gravitational force, and it looks like that, mg. I can write that as the force 0, negative mg, 0, right? It has a negative y component. We write mg as a vector, but the y component of g is negative. That's why. That's why that's negative. So now I have those two things. I'm going to erase this stuff and just write what I need. I like to have plenty of room for options, right? For happy space. So I have delta R is 0, negative H, 0. I have F is 0, negative mg, 0. So let's go ahead and calculate the work. That's going to be F dot delta R. And how do we calculate the work? In case you don't remember, we take the x components and multiply them together. We take the y components and multiply them together. And we take the z components and multiply them together. And then we add all those up. So let's write that out explicitly. So here I have 0 times 0. That's not a dot because these are scalars. That's a times. Now I have plus negative h times negative mg. And then I have plus 0 times 0. So 0 times 0 is 0. 0 times 0 is 0. Negative h times negative mg is going to be mgh, and that's my work. It's a scalar, and in this case it's positive, right? When we write g, that's the magnitude of the gravitational field. Don't put negative, but this is positive. So going back to the work energy principle, if my work is positive, my change in energy is positive. So that means I'm going to be increasing energy of the system. That makes sense. As that ball falls, it's going to speed up and increase in kinetic energy. Okay, so when we have our work, we can go ahead and write down our work energy principle. So I have, this is going to be the change in kinetic energy, which is K2 minus K1. So now I can put it all together. I have mg, h, that's my work done. It's going to be equal to 1/2 mv2 squared, that's my final kinetic energy, minus 1/2 mv1 squared, that's my initial kinetic energy. And I want to solve for the final velocity v2. Okay, so how do we solve this equation? Well, first of all, I know up here, you can barely see it, but I said the initial velocity was 0. So if v1 is 0, then that's gone. So now I just have this. mgh is 1/2 mv2 squared. I can divide both sides by the mass. And I want to solve for v2, so I'm going to multiply both sides by 2. So now I get v2 squared is 2gh. And now I can take the square root of both sides. And there's my answer. Okay, so let's just check a couple things. Number one, I never said what the energy for work and energy was, the units. That was on me. I'll tell you that in a second. So here I have 2 is just a number. G is in newtons per kilogram or meters per second squared. And then I multiply by h. I get meters squared per second squared. I take the square root. I get meters per second. So that does indeed work. But let's just take a little aside here. The unit for energy is the joule. And 1 joule is equal to 1 kilogram meter squared per second squared. Okay, so you got that. But there we have our answer. How fast was it going at the bottom and using the work energy principle. There was something else I was going to say. Okay, let's find the work one other way, right? What if I don't want to write these vector things? I don't want to deal with that. That's fine. I don't have to do that. Let's just erase all this stuff. Let's do it again real quick. What if I say work is F delta R cosine theta? I don't want to write these as vectors. That's fine. So what's the magnitude of the force? And these are just magnitudes, so it's just mg. What's the magnitude of delta r? Well, how far did it go? Well, it went h, right? And I'm only care about the y direction. But it doesn't matter. It is h. Okay, and I'll show you how this will change in the next problem. And then I need theta. So what's theta? Theta is the angle between the force and the displacement. So in this case, it's moving down. Delta r is down. The force is down. So those are both in the same direction. So theta is 0. So work is going to be the force, mg, times the displacement, h, times the cosine of 0. And so the cosine of 0 is 1. So you get mgh. So now I go back to the same thing, and I have work as mgh, and that's the change in kinetic energy. And after that, the whole problem's the same. One more thing. What if I had picked, going back to the beginning, what if I pick up here? No, I'll do that later. Let's do that later. I think that's good enough. If I choose that as my system, then that's fine. I'm done with the problem. Let's look at one other problem, okay? I do want to make a version of this to show you something cool. Suppose I have, instead of a ball falling a height h, it slides, it's not rolling, it slides down an incline. So this has a height h and it goes down there. And I want to find the velocity at the final point. So v1 is 0, and I want to find v2. Well, let's again choose the system of the ball. Now I need to think about what forces can do external work. And now there's actually two forces acting on the ball, right? I have that at any particular point, I have the downward gravitational force mg, and then I have the normal force N. And so we did this problem using Newton's second law, and we found the acceleration and all that stuff. But we're going to do it again. So if the system is my ball, I have two forces that can exert work. So let's just deal with them one at a time. Let's start off with the normal force. Work N is going to be the normal force. I'm going to write this in the scalar version, N, and then I have delta R cosine theta. So in this case, I need to find this distance right there. That's my delta R. Well, I'm going to call this the angle alpha, just to be different from theta. So if that's the angle alpha and that's h, then I can say delta R is going to times cosine, sine of alpha is going to be opposite h over delta R. So delta R is going to be equal to h over sine of alpha. So that's going to go in right there. And we're going to use that in a little bit. But this is the angle theta, and this is the angle between the direction it's moving and the direction of the force. And notice right here, theta is 90 degrees. So what happens as this ball slides, doesn't roll, slides down the incline, the normal force doesn't do any work. I don't even need to find the magnitude of that normal force. I know that it's perpendicular to the direction it's moving, so no work done. Okay, so this is going to be equal to 0. That's good. Now we can find the work done by the gravitational force. So here I do need something. So let's say, so work done by gravity is going to be the gravitational force times delta R times cosine of theta. So I know mg, I just found delta R, so it's mgh over sine of alpha times cosine of theta. Now here I have a right triangle. That's alpha, that's theta. Theta is the angle between the direction it moves, right? So if I want to take the cosine of theta, that's the same as the sine of the complement. So these two terms cancel. You could, if you put in a numerical value and you don't believe me, put in numerical values and you can do it. So I get the work done by gravity is mgh. Wait, That's the same thing as what we did before, right? If I go back and I say work is mgh, and that's delta K, and that's 1/2 mv2 squared minus 1/2 mv1 squared, and that's 0, then V, the same problem, right? V2 is the square root of 2gh. So this problem looks like that problem. And from an energy perspective, it is the same. The velocity of the ball here is the same as the velocity of the ball there. But they are different for one reason, because this ball is moving that way, that ball is moving that way, but they have the same speed. They're going to take different times to get to that point, and they're going in different directions, but that's the limitation of the work energy principle. It doesn't tell us direction. It doesn't tell us time. It's a different way of looking at things. So it's easier, but it's not as complete. Okay. Let's go back to the ball, and now let's pick a more complicated system. System. The ball plus the Earth. So this Earth over here is part of my system. If that's the case, then the Earth pulls on the ball, but the ball pulls on the Earth. So the gravitational force is no longer an external interaction. We no longer have work done by gravity. And in fact, there's no external forces, there's no external interactions. So the work would be 0. But how can that be? If the work is 0, how can it be that the ball speeds up? We know the ball is going to speed up. Wouldn't the change in energy be 0? Yes, the change in energy would indeed be 0. But we have a new type of energy for our system. So here we have a new energy. I'm going to call it UG as mgy. We call this gravitational potential energy. Now, this is an intro class. This is not, I'm writing out the whole thing. This is not like super duper physics, right? We're just talking about algebra-based physics. And so there are some rules about when you can make things a potential. The idea is that it has to be a conservative interaction, a conservative force. But what's really happening is you're calculating the work done by gravity and then moving it to the other side of the equation. So this potential comes from looks similar to the work done by gravity. We should get the same thing. Okay. Another thing that we're going to see is that the potential isn't really important. It's the change of potential that shows up. Okay, and where there's other types of energy, I think at this level we just say, okay, gravitational potential. I'll show you a different version at the end. Okay, finally, the potential energy is a property of the system. It's not, the ball does not have potential energy. The ball plus Earth has potential energy. That's a really important point that a lot of books just say, oh, the ball has potential energy. Okay, so just be very careful about that. Be very careful about when you're reading these books and what they say, because they don't always think things through. I thought things through because I read some other books. Okay, so if that's my system and I have that energy, I have two types of energy. So now I can say the work is the change in kinetic energy plus the change in gravitational potential energy. And we know that's going to be 0. Okay, change in, going from point 1 to point 2. So let's go ahead and write this out. We do need, since the gravitational potential depends on the value of y, I need to pick where y is equal to 0. So let's go ahead down here and say y is equal to 0 at the bottom again. So I said the work is 0. That's going to be K2 minus K1, change in kinetic energy, plus UG2 minus UG1, the change in gravitational potential energy. Now I'm going to put in my expressions for those. I have 0, 1/2 m v2 squared minus 1/2 m v1 squared, that's just my change in kinetic energy, plus mgy2 minus mgy1. Now, in this equation, there are two terms that are 0. that I can cancel, that I can just drop out. And the first is this one, right? Because the initial velocity is 0, then this term is going to be 0. And then since I ended up at y equals 0, I said y is 0 down here, that's going to be 0. So now I have 0, 1/2 mv2 squared minus mgy1. y1 is actually, if that's 0, y1 is h. So now I can add that to both sides. I get 1/2 mv2 squared equals mgh. The mass cancels, multiply by 2, take the square root. Shouldn't be a surprise, 2gh. That's the exact same thing I got before, right? Because it shouldn't matter what I pick as my system. The final result should be the same thing. We can measure the final velocity. So it shouldn't matter how fast it's going depending on how I calculate it. It should be the same thing. Okay. What if I picked, let's do the problem again. What if I picked up here is y equals 0? What would happen to the problem? Well, let's go back up here. Really, the only thing that's going to do is change these potentials. So now I have 0 is 1/2 mv2 squared minus 1/2 mv1 squared. Now my final gravitational potential energy is going to be y is going to be negative h. So it's going to be minus mgh minus mg0. So that's still 0. That's 0. I get 0 equals 1/2 mv2 squared minus mgh. And it's the same problem. So you see that picking a different coordinate system doesn't change the answer because we're dealing with changes in potential energy. Okay, that was a more complicated system, but let's do an even more complicated system because you're thinking, well, why would I choose, when do I have to choose the Earth as part of my system? Do I have to use potential energy? And the answer is no, you don't have to. You can always do it either way, but sometimes it's easier than the other way. So, and how do you know which way to choose? Well, it's experience. You just got to do a lot of problems, right? You practice a lot of problems and you get better at this. Let's look at one more problem, and then I'll tell you 2 other forms of energy. We're not going to deal with them in this video because it's just a simple. I'll tell you 3 forms of energy that show up. But the key is system. Pick your system. Here is a very complicated problem that shows up in books, and books are like, oh, it's easy. It's not easy. So here I have a mass m on a string of length L, and let's say this angle is alpha, just for simplicity. And I want to let it swing down. I want to find out how fast the ball is going right here on the string. So if you want to solve this with Newton's second law, you're in trouble, right? Because let's just draw the forces on this. I know I have the gravitational force, mg, and then I have the tension going that way. And the problem with this problem is the tension. That tension is going to change directions as it moves down here, and it's going to change magnitude. The tension is a force of constraint. It applies whatever force it needs to keep the ball moving in a circle. And so you really can't, there's no equation for it. So it makes it very, very difficult. We don't know how long it's going to take to move down there. There's a whole bunch of problems. It is solvable, but you got to do some tricks. And you don't want to do those tricks. Okay, so what if I choose, I want to use work energy, and I choose the system, and so this is point 1 and that's point 2 down there. The system of just the ball. Okay, that's fine. So I can say the work is the change in kinetic energy. If it's a ball, it only has kinetic energy. And then I think, what external interactions do I have? Well, let's just look at one, and then we'll change our system. And that one interaction is the gravitational force. How would I calculate the work done by the gravitational force? The problem is that the angle between the displacement, delta r, changes, right? So it's not moving in a straight line. So I can't do the work done by gravity. I can, but you don't want to, okay? So that becomes a problem. Well, we can fix that problem by adding in the Earth. So if I do that, then I have a gravitational potential energy, and my work done by gravity is 0. So that fixed the problem, right? So it's not moving in a straight line, so I really don't want to do that. Now I still have the work done by tension, which would be the tension delta R cosine, I'll call it theta. And that's a non-constant force. So this is like, should set off alarms. Watch out, okay? But it turns out that we know what this is. Because although the tension changes direction and magnitude as the ball swings down, delta R is always going to be moving perpendicular to the tension. So the thing is that this is always a right angle, even when it gets down here. So theta is 90. So I don't really care what delta R is. I don't care about that because I'm multiplying by 0. So the work done by the tension is 0. So by choosing the Earth and the ball as my system, then I have no work done on it. So overall, I have this. 0 is the change in kinetic energy plus the change in gravitational potential energy. And I can do that problem. So let's do it. Okay. So we have the system of the ball and the Earth. The work is 0. Okay, well now we need to pick some things, right? If I have potential energy, I have to pick a y value. Where am I going to pick my y is equal to 0? There is no wrong answer. There's an easier answer though. And it may seem counterintuitive, but I'm going to pick y is 0 up here. So this is my y1, that's my y2. So let's write down what we know. I'm going to say 0 is 1/2 m v2 squared minus 1/2 m v1 squared plus mgy2 minus mgy1. Are any of those terms 0? Well, I don't know about v2. I'm trying to find that. But I do know the initial velocity is 0, right? I've released this from rest right here, so that term's 0. Is y2 0? No, 0 is up there. Is y1 0? No. So just that one. Okay, let's go ahead and find these values for y2 and y1. y2 is actually pretty easy. y2, if this has a length L, that's straight down there, so that's going to be negative L. But what about the y2 value of this one? Well, if I draw a line straight over, that's bad, but that's my y value right there. So y1 is going to be equal to, it's negative, the length of this L times cosine alpha, I'm sorry, right? Because it's the adjacent side of that triangle. So let's put all this stuff in. So now I have 0, 1/2 m v2 squared plus mgy2, y2 is negative L, minus mgy1, which is negative L cosine alpha. First of all, I can divide both sides by the mass. I can multiply both sides by 2. So let's do that. I get 0 v2 squared plus, this is going to be minus, right, because there's a minus right there, minus 2gl, and this one's going to be minus times a minus, so it's plus 2gl cosine alpha. Now I can add that to both sides. I can subtract that. I get v2 squared is going to be 2gl minus 2gl cosine alpha. If you want to factor that out, and yes I do, I get 2gl times 1 minus cosine alpha. So that's v squared, and then if I want to take the square root of both sides, that's my final velocity. Does it have the right units? Meters per second squared times meters is meters squared per second squared. 1 has no units, cosine has no units. So I'll take the square root to get meters per second. Check. Now, you'll notice this distance right here is L times 1 minus cosine alpha. So if I drop the ball from here, it would be going the same speed as if I release it from rest right here. But of course, the difference is it takes a different amount of time and it's going in a different direction. Okay, so work energy doesn't give that to us. But this is a pretty complicated problem if you want to solve it exactly. But if you just want to find the speed, it's not too bad. Okay, let's talk about energy. So I just want to list out section summary. How about that? Section summary. So we have this. Work is the change in energy. Work is F dot delta R equals F delta R cosine theta. And that depends on your system. You got to pick a system. And I did leave some stuff out. Okay, I know that. Now, what about energies? So we have kinetic energy. Notice that two things. One, we're always dealing with a change in kinetic energy. It's delta K. That's kind of a big deal. And that can bring in some problems with, reference frames and things like that. I'm just letting you know. Okay. But since mass is positive and we're squaring the velocity, it can never be negative. You cannot have negative kinetic energy. You can have a negative change in kinetic energy, though. Okay. And then we have gravitational potential energy, mgy. Again, we don't care about y. We care about the change in y. We care about the change in potential. There's another type of energy that shows up. If you take a spring and either stretch it or compress it, we get spring potential energy, 1/2 K S squared. So here's my spring. Do I do it? Yeah. And if you either stretch it in S or compress it in S, and that's the spring constant K, then I have energy stored in that spring. Another type of energy, remember that we have the gravitational force was mg. But we also had this Fg is g m1 m2 over r squared, that universal gravity, which we wrote as a scalar most of the time, even though it's a vector. Well, that goes with this potential energy, but it's really this potential energy that matters. So we have universal potential energy. Ug is negative g m1 m2 over r, and the negative may not make sense. It doesn't matter. It's a change in potential that matters. Okay, so that's my real gravitational potential energy. So I have kinetic energy, close to the surface of the Earth potential, real gravitational potential, spring potential. Another one that does show up is thermal energy. Delta E T is mc delta T. So that's a change in temperature. That's the specific heat capacity, and that's the mass. So if you add energy to an object, it can increase in temperature, but it depends on the mass and the type of material that it has. About the amount of energy that it changes. Okay, so there's a bunch more stuff. There's stuff about work done by friction, which is really weird to think about, and things like that. But that's a good intro to the work energy principle. Oh my gosh, I did 43 minutes. If you watch this whole thing, you need to give yourself a double high five. Wait, double. There you go. Okay, that's that. Talk to you later.